Morning, Wendy.
Morning.
So today, I probably you're the only one going to come in. So I'm just going to be probably kind of like lecturing today. So feel free to stop me.
Okay.
I'm not going to collect that lab. I'm kind of hoping you did the lab and played around with it a little bit, but I'm not going to collect it from you. There's not going to be like more homework or anything, but I do kind of want to get you prepared for the makeup. So in a way, I'm hoping that this will be kind of a silver lining. I don't want you to think of this as being a penalty. There's going to be a final exam, but it's going to be, think of it, the final exam is going to be more of a practice, that if you're just making some attempt, then whatever grade you got right now, that's going to be the grade you get at the end of the of the year. Just like everybody who took the test on Monday, it's not really, I hope that you don't see it as a penalty. It's going to be practice for the makeup so that you're even more prepared, but it's not going to, I don't think it's going to be more effort on your part other than maybe come into the Zoom sessions.
Okay.
All right. So everything going okay for you?
Yeah.
Okay. All right. Hey, did you ever find out if you're going to be able to go to the academy next year?
Yeah, I'm accepted. Yeah.
You accepted? No.
Um,
Congratulations. Nice.
Thanks.
Okay, so I'm going to go ahead and get started then. Let me share my screen with you. So I'm just going to start. I think maybe I'm just going to go ahead and talk about 2D collisions because you might see that on the makeup test. Um, and I'm hoping that you got the data and we actually talked about it already, that you saw that momentum was indeed conserved both in the X direction and in the Y direction. And so I'm not sure. Let me see if I can pull up that PhET site because I want to do one type of collision that's, if they do a two-dimensional collision, it would probably be one of these types of two-dimensional collisions. If I can find it, where's it at? And of course it doesn't work in Chrome, so I'm going to have to open up Mozilla. Okay, all right. All right, let me go to advanced here. What I want to do is I'm going to change the mass to be the same mass, so 1.5. It could be 1, it could be 2, whatever. And I think what I want to do is I want to have this object kind of coming in here like the straight. If I can, I'm going to try to make it go straight. And this one here, I'm going to have slightly off center. So not exactly on center collision. It's going to be an off center collision. And I want to make the velocity of the green one 0. So it's just sitting there. And what I want you to do is I want you to watch this. So I'm going to hit play. And I want you to look at the angle between those two vectors. See if you can kind of figure it out. What does that angle look like it is?
90.
Exactly. And let me see if I can do another one. In fact, if you ever, when you go to college, maybe or I don't know if the academy, if they have pool tables or not, but you can make lots of money. So you can kind of, I'm not saying you should do that, but that's one of the things that you can kind of use your physics is that if you don't put any, it's called English on the ball, you don't spin it at all, those two pool balls are about the same mass. And if you hit them slightly off center, if they have the same mass, the angle should always be 90 degrees between their collisions. Let's see, I can try, oops, no, that's not what I was trying to do. Dang it. I can even put it up here like this. Let me make this 0 again. This is 0. I'll change the mass. Maybe I'll make it 3 and 3 and hit play again. You can still see it's 90. I'm not sure. I've never tried this. Let's try, I wonder. Wonder what would happen if they have different velocities. I have to make sure they hit though. Well, that doesn't look like 90, but if one of them is just sitting there, then it is 90 degrees. So it's kind of interesting. So anyway, let me stop sharing that. And we're done with this too. I want to kind of start a PowerPoint that has notes. I think just kind of watch it. You don't need to take notes, just kind of watch. And if you want me to share the PowerPoint with you afterwards, you can. Or I can, just ask. Okay, so let me stop sharing for a second. And oops, okay. All right. I don't know. Okay, this. Come on, dang it. Okay, I got it. 2D. All right, so I think there's a way to share. There we go. Okay. All right, so let me go ahead and start this. All right, so for instance, for the Large Hadron Collider and for Fermilab up near Chicago, what this picture is here is kind of what they called back in the olden days bubble chambers. And what a bubble chamber had was it had usually it was, I think it was liquid helium. And when these particles would go through the liquid helium, it would ionize some of those particles in there and kind of cause them to start to bubble. So that's where it came up with this bubble chamber. And what the person looking at it, what they saw was almost like if you ever looked up the sky and you saw those jet contrails, you know, those little lines of white that come out the end of the jet. That's kind of what the people saw. They saw all of a sudden like this thing just jetting through with these bubbles after it. Well, that's what this picture is. So you see these lines that are kind of on there. Well, that's a picture of these little tiny bubbles, and those dark lines are actually the bubbles. And they weren't there at first. It was just clear, and then all of a sudden, boom! This just came out of nowhere. Well, what those bubbles indicate is that there was a particle that was traveling along there. And so I'm kind of hoping you see there's actually a couple Y's, but there's this big Y and there's another Y over here. You also see these other kind of concentric, almost like part of a circle there, a bunch of parallel lines. Those are also particles, but those other ones that just kept on kind of moving on, they didn't hit anything. The two Y's were actually a collision. And so I'm going to look down here at this lower one. What that was is there was a proton that was moving through here really fast, and it hit another proton that was just sitting there, kind of like the billiard ball example. And what happened was then the two billiard balls, the two particles, the two protons, kind of veered off one another. So in this problem, there is a proton traveling with a certain speed. It collides elastically with a stationary proton and a hydrogen particle. Oh, so it was liquid hydrogen, sorry. One of the protons is observed to scatter at a 60-degree angle compared to the original path. So if you look at the concentric lines here, you'll see that the one is kind of a 60-degree angle from the original direction. It wants to know what angle will the other proton, that's on the other side, you can probably estimate it, but we're going to do some calculations here to figure out what that angle is. And we're going to try to find out what the two velocities of the two protons are after the collision. So it seems like, wow, how do we solve that when we only know two things? The truth is we also know the mass of the proton, we know that. But we only know those two things. How are we going to find the velocities of two particles and the angle of, so that's like three unknowns. Well, the hint is we actually know one other thing because it says the word elastic, which means that energy is conserved. So we have momentum being conserved. It's and it's also kinetic energy is conserved. But that momentum being conserved is actually in two dimensions, both in the x dimension and in the y dimension. And so I'm going to go ahead and set up equations here. And again, if you want me to share this PowerPoint with you at the end, no problem. You know, just let me know and I'll share it with you. The likelihood of you seeing this on the test, I don't know, because there's only going to be two problems. Probably not very likely, but I mean, maybe. So I just want you to see how it's done. I don't know that you necessarily need to analyze it too closely. Just kind of follow along to see if, that it makes sense to you, that you think you could do it, kind of a thing. So there's only three ideas here we're using. Energy is conserved and momentum is conserved in the x direction and in the y direction. So that's our three equations. That's going to help us find our three unknowns, the two speeds and the angle. So in the x direction, the particle, which I'm just going to call the mass of the proton, I'm just going to call it m for now, and we'll plug into it later, is originally going at 8.2 times 10 to the fifth meters per second. Then after the collision, it veers off at 60 degrees, and the other proton that it hit, same mass, goes off at some other angle, theta b, I'm going to call it. We don't know what the two final speeds are, VFA and VFB. We don't know what those are. In the y direction, we're going to assume, based on my coordinate system there, we're going to assume that the initial momentum is 0 in the y direction. But afterwards, you can see they're both going in the y direction slightly anyway. And so for the original particle, it veers off in 60 degrees. And for the other particle, it goes in the other direction at some unknown angle, theta b. We also have from energy conservation, because it says elastic collision, it's 1/2 the mass of the particle originally moving at 8.2 times 10 to the fifth meters per second. That squared has to be equal to the sum of the two final kinetic energies. So there's a lot of unknowns here. Looks like the mass. The truth is we know what the mass is. We can plug into it, but we don't know the angle. We don't know what the two speeds are. But luckily, we also have three equations, three unknowns. We should be able to solve this. Okay. So I'm going to divide both sides of all three of these equations by the mass, and that will cancel it, so I don't even have to look that up. And in the kinetic energy equation, since there's a half on both sides, the half drops out. And rewriting those three equations becomes 8.2 times 10 to the fifth equals v cosine 60 and v sine of the unknown angle. I hope that makes sense. Oops, let me go back. That's what it was. The masses drop out, and so it becomes this. Hopefully that makes it a little clearer of the three unknowns that we have. So we just need to figure out how to combine these in such a way that we can find for the unknowns. The truth is, this is usually kind of a difficult problem, I would say even for me, because you start thinking, well, I can solve this pretty easy, three unknowns, three equations, I can solve it. We have to use the idea that sine squared plus cosine squared equals 1. So we have to use that trig identity, which isn't hard, that's pretty easy. But that means we need to rearrange the top two equations for sine theta b. We need to get it in terms of that so that we can then square the two equations. That's where I'm going with this. Because when I do that, it kind of gets rid of that one unknown, because I have to get rid of an unknown somehow. So rearranging the top equation, solving it for VF b cosine of theta b, and the second equation, I get those two equations. So where I'm going with this is, again, using that trig identity, where I'm going to square both of them. And so now squaring, well, here's the two equations, squaring both of them. There's the top equation squared, and there's the second equation squared. Again, stop me if something doesn't make sense. Basically, I just want you to watch through this and say, could I do this myself? The trick to this is realizing you have to use sine squared plus cosine squared equals 1. Now add both equations, and so now I get this. Notice on the right-hand side, when I factor out the VFB squared, I have sine squared plus cosine squared, and that's going to just simply be 1. And so I'm left with this quantity. Now I went ahead and squared out the left-hand side. And you'll notice on the left-hand side, there's also a sine squared and a cosine squared. So I'm going to kind of regroup those a little bit. So this is mostly just algebra stuff going on here. So regrouping those, and I get finally a little bit nicer of equation at the bottom there. So notice what I did was I eliminated the theta b, got rid of that. The truth, on the left-hand side, did I really need to get rid of the sine squared cosine? No, because I know what that angle is, so I could plug it in. But I kind of prettied it up a little bit. So now I have these two equations. The one on the right-hand side comes from energy conservation. That was equation 3. And so notice both of these equations are equal to VFB squared. And so I can set these two equations equal. And finally, I'll be able to figure out one of the unknowns. So that's where I'm going next. And the unknown I'll be able to solve for, if you look at this, I know everything except for VFA. And so I just need to combine like terms, lots of algebra again. I can get rid of one of the terms there. And notice there's a VF squared on both sides, so I subtract that over to solve. And I can eliminate the -2. I can divide by VFA. And finally, I can solve for VFA. And really, that's the hard part. So once I know VFA, I can go ahead and plug that back into equation 3 and solve for VFB, and then I can go back to equation 1 or whichever equation is easiest to solve for the angle. And for VFA, I got 4.1 times 10 to the 5th meters per second. So that was the final speed of the original particle after the collision. Plugging that into equation 3, I get VFB is equal to 7.1 times 10 to the 5th meters per second. So that's the proton that was stationary originally that got hit and kind of got knocked into the other direction. And now finding the angle, I used equation 2 because I thought that was the easiest one. You could have used equation 1, doesn't really matter. And plug in, and I got an angle of 30 degrees. But what I want you to notice is this. Both of these protons, just like in the very beginning, the simulation I showed you, both of these protons have the same mass. Notice what the angle is between their separation. The one's going off at 60 degrees and the other one's going off at 30 degrees. So those particles, whenever they're equally massive and they hit off center where one of them's kind of just sitting there, and it's elastic. That's the other thing that's important. And it's elastic. Their angle separation has to be 90. The reason why I'm pointing this out and stressing it is if you know that, that could really help you out a lot. Imagine like you're like, hey, I remember this is elastic and I know the angle here is 60 degrees. I know what the other angle is. It's 30 degrees. And if you pop that in right away, bang, you have the answers a lot faster. Wendy, any questions on that?
No.
All right, so I don't know if that comes up or anything, but just in case, and if you want me to share that PowerPoint so you can go over it slower, let me know. Let's see, the next thing that I want to do, let's see. Oh, by the way, if you want to do it, you don't have to do it, but there are 4 practice problems here doing this conservation momentum in 2 dimensions. In fact, let me go ahead and pull it up so you can see it. Come on, hey, what's taking so long here? Oh, there we go. There's only 4 there, but you can kind of practice them a little bit. Now, this 4th one is not really conservation momentum in 2 directions, but it's nice. It's a good AP problem because it's conservation momentum and conservation of energy. So it's a good practice. And the reason why I'm kind of pointing it out is because I've given you the answers all mixed up down here. So it's good practice. There's only 4 of them. So, something to look at. Don't have to, don't feel like you need to. Just a suggestion. Now I also want to talk about one more thing since I have you here, captive audience, is I want to talk about velocity dependent forces. This is another thing that you could see. I wonder why it says my screen. Can you still see my screen, Wendy?
I can only see the PowerPoint.
Oh, sorry. Duh. Okay. Stupid. Okay, let me figure out what to do here. Okay. Sorry, my bad. Let me go back over that again. Can you see my screen now?
Yeah.
Okay, so let me pull this back up again. I'm sorry. So there's 4 questions here, and there's mixed answers. So I'm recommending it, but you don't need to do it, okay? The next thing I want to talk about is velocity-dependent forces, because again, that could be on the AP test. When I say velocity-dependent forces, I'm talking about air resistance. So I kind of want to do a PowerPoint on that. But before I do that, again, I want to show you that there are practice problems here. Don't have to do them if you don't want to. I really don't know how likely it is you'll see these on the AP test because they are a little bit more challenging, and I don't know if it'll be there or not. But this first page in this is kind of a cheat sheet. I don't know why there's a black square here. This should have been a force diagram if you're dropping something. When you first drop it, let's say a sheet of paper, when you first drop it, there's no air resistance, it's just a weight force down. But then as time moves on, so moving from left to right here, there gets to be a bigger and bigger drag force. And eventually when you get all the way over here to the right picture for the force diagram, and you reach terminal velocity, and the drag force equals the weight. And so I have the equation here, W equals D. If you were plotting the velocity versus time, you'd kind of get this asymptotic curve that goes up to some value. That value is called the terminal velocity. And that terminal velocity, assuming if you look at the equation over here, W equals D, that means at terminal velocity. That means the mg equals, usually the drag force is related to the velocity. It's the faster the object's moving, the bigger the drag force. So it's a linear dependence, which means that the terminal velocity, if you solve that for V, would be equal to mg over B. And so kind of gives you that. The equation, if you're like, what is the equation of this? This is actually kind of a e to the something relationship. In fact, it's given down here. So sometimes on the AP test, again, I don't know if it'll be on yours, but sometimes they have you derive the equation, but sometimes it might be just easier if you understand that this is what the relationship would look like. So imagine putting in right here, the time is 0. If you put a time as 0, that would be e to the 0, which is 1. And so you have 1 minus 1, and so the initial velocity would be v times 0. 1 minus 1 is 0. And so you'll see you get 0. If you put t, a very big number, like t equals infinity, that's going to be e to the negative infinity. Well, negative infinity would be the same thing as 1 over e to the infinity, which is a big number. So 1 over a big number is 0, basically. So it's going to be 1 minus 0, which is 1, and you reach some terminal velocity, vt. So that equation exactly matches this graph. And sometimes I think it's better just to kind of memorize that equation, or maybe even put it in your calculator. So this is kind of a cheat sheet for velocity-dependent forces. But there are problems here, and especially the last ones here. These are actual AP problems from past years. So the only reason I'm mentioning it is, again, if you're wanting to study, I have the answers here, but I only have the answers to those AP practice problems that are worked out. I'm not going to click on it just in case you wanted to practice or something. Anyway, I want to go ahead and do a quick PowerPoint on velocity-dependent forces. And again, I guess the final exam is for you would be next Monday at 9:30. It's going to be a Zoom session, and what I'm planning on doing is I'm planning on giving you a couple AP problems, and just to practice, and you'll have basically the same amount of time you have on the makeup. And it's not like, don't be stressing about this. You know, I just want you to do the best. The way I see it is, the students who did the test yesterday, they just did the best they did. So as long as you tried on Monday, then you're going to have the same, or yeah, Monday, you're going to have the same grade you have right now. Okay. So don't be stressing about it. Don't feel like you need to study for it. Okay. It's just good practice, I hope. That's the way I see it. Okay, so I'm going to go ahead and get started on the velocity-dependent forces. Oh, wait a second. Of course, you can't see this. Dang it. Sorry. This was actually a video I took of dropping some coffee filters. And there's different coffee filters. I have them stacked. So I have stacks of like, let's say one coffee filter just by itself coming down. And then I have like a stack of two of them put together, dropped together, which means double the mass, double the weight. 3, 4, 5, and 6, let's say 6 coffee filters all stacked together and drop. Let me go ahead and play the video so you can see what happens. Okay, I don't think that's a big shock. You saw that that first one that came down, let me play it again. It came down pretty quick, which means it travels the same distance in less time. All of them, by the way, are not accelerating. They've all reached their terminal velocity. But that first one covered that distance in less time, which means it has a bigger terminal velocity. So the slowest terminal velocity, the one that was going very slow at the very end that finally hit, that was just one coffee filter. So from that video, we could actually kind of figure out the relationship for the drag force. Remember I said it was dependent on the velocity, directly dependent on the velocity? Sometimes it's not directly dependent on velocity. Sometimes it's dependent on the velocity squared. It just depends, okay? All right. So here we're going to say it's dependent on the velocity. So that was an example of something falling through air, which is a fluid, but it could be just falling through a liquid fluid too. So as this thing falls, whether it's through air on the left or through a liquid on the right, so let's say a ball bearing falling through oil, what happens is if you look at the force diagram there, at first there's only a weight force on it, but then as it starts to fall, this drag force starts to get bigger and bigger. Eventually it reaches what's called terminal velocity. Terminal velocity means it no longer accelerates. So F equals ma is equal to 0, and the drag force equals the weight. Now we've already done some of those problems earlier in the year, conceptual, where it's less, but we've done some actual computation problems when it was equal. And looking at the graph of this kind of looks like that. So I kind of gave you the cheat sheet in the beginning, but this is kind of going over a little bit slower and more detail. And the relationship would kind of look like that. I want to do a few problems, and again, interrupt me at any time if there's not something you understand, and I would be more, you don't need to copy notes on this, just kind of follow along. If there's any of this you would like to, if you want me to share the PowerPoint with you, I will be glad to do that. I will say this right now, this velocity dependent forces is some of the most difficult stuff because it has calculus involved. So again, I don't know if it's very likely that would be on your test, the makeup test for you, but I at least wanted you to be able to see it. Even if you can't do the calculus, you should be able to answer some of the stuff. Like if they had a problem like this, you should be able to get some of the answers because eventually it becomes terminal velocity and you can set them equal. All right, so for this one, we have a raindrop that's falling and eventually it reaches terminal velocity of 9 meters per second. And it tells you the drag force is directly related to the velocity. And we're supposed to draw two free bodies for the raindrop. Okay, well, one's going to be when the velocity of the raindrop's less than the terminal velocity, and one's going to be when it's equal. So that should be pretty easy to do. Less than terminal velocity means the drag force would be less than the weight force. And when it reaches terminal velocity, they would be equal. They're balanced. Okay, so if you wanted to figure out up in the equation where it says D equals B times V, which of those force diagrams would you use? I'm hoping you'd see that the one that would be super easy would be the one on the right. The drag force is equal to the weight. And then I could just set BV equal to mg and then solve it. And so I get B is equal to mg over B. That should be super easy. There's no calculus there at all. The calculus is in that first free body diagram. Okay, so now I gotta move this because I can't see. Okay, complete the net force equation for the first free body diagram. So there's nothing special here. This is stuff that you know how to do already. And so that would just simply be F net equals the weight minus the drag force. For the next part of this, it says using the equation that we have above, we need to write a differential equation. So sometimes students who aren't in calculus, they get freaked out by that, but it's not that hard. There's no calculus here, not really. The differential equation would just simply be plugging in what F net is, which is ma, and realizing that a is really the derivative of velocity. So plugging in for what a is, a would be equal to dv over dt. Now I did some fancy stuff over here with algebra, but that's not even really necessary. So I could have actually done this first step way up, or this last step way up here. I could have wrote dv dt equals g minus bv over m. I could have had it way up there. Now, the reason why I factored out this negative b over m is because if you remember, there was that exponential e to the something. That's where I'm going with this. So again, you know, if you have any questions, kind of say something. So what I want to do in this next step is I want to integrate that equation to determine the velocity. This is where it starts to get hard. This is the calculus stuff. So if I want to find the velocity, what I need to do is I need to get all the velocity terms on one side and the time terms on the other. So if you look on the right-hand side, this is why I simplified it a little bit. I have a quantity that has v in it. So I'm going to divide both sides by that quantity. And then what I need to do is I need to go ahead and integrate this. And what I'm integrating it from is the initial speed, which is in this case 0, because we're dropping it, to some speed that I don't know. I'm going to say some velocity at time t. That means on the right-hand side, I'm integrating from time 0 to some time t. It turns out on the right-hand side, that's really easy. I don't see a t term there, so it's just simply going to be negative b over m times t. On the left-hand side, that's where it's a little bit more difficult, but I think, Wendy, you're in calculus, right?
Yeah.
So on the left-hand side, it's kind of like having dv over v. Well, I'm hoping you see that's a natural log function. And so integrating that, I would have natural log of, I'm doing this bottom quantity here, of v of t, because I have to plug in that top boundary, minus mg over b, minus natural log of, well, I have to plug in 0 for b, so 0 minus mg over b equals the right-hand side, which is kind of easy. Okay, the next thing I'm going to do is I'm going to use, again, stop me if there's any questions you have. I'm going to use property of logs. When you subtract logs, that's the same thing as dividing. Oh boy, I can't see again. Dang it. Things constantly in my way. And so it kind of looks like this. What I'm going to do now, I don't even know the name for it. I'm going to call it exponentiate. I'm going to exponentiate each side. I'm going to take e to the whatever on both sides. I don't know if there's a word for that or not. And when I do that, it kind of gets rid of the natural log on the left-hand side, and I have e to the negative b over m times t there on the right-hand side. And then finally, I just need to rearrange this, solving for the velocity v of t. And when I do that, this is what I get. Remember that mg over b was the terminal velocity. In fact, let me go back. That was the terminal velocity. So that's why I said on my cheat sheet, it might be good just to memorize that equation or put that equation in your calculator, because that's the equation right there. And it always has that function. So anyway, and we found out what that terminal velocity was already. And so that's the relationship I get. Okay. And I can't see again, dang it. Can I move this over here? Nope, can't. All right. Determine how much time is required. to reach 63% of the terminal velocity. So what I can do is I can do 0.63 times the terminal velocity of both sides, or on the left-hand side, and I can go ahead and solve this now, divide both sides by VT, and rearrange it, and I can take the natural log of both sides, and I know what the terminal velocity is because I found that earlier. I think that was 9 or something like that. And I can solve for the time, and I get around 0.89 seconds. What time is it? I don't want to go over my time, sorry. 9:53, 9:20. Okay, I think we're going to do a few more minutes, and that'll be it. Okay, this is another one. This is also a velocity-dependent force. It's not something you're dropping, though. A boat, or even a bicycle, you know, you're coasting for a little while and you start to slow down. That would be a velocity, and that's probably because of air resistance or something like that. That would be a velocity-dependent force. This is a boat moving through water, turns off its engine, and it kind of coasts for a little bit, and it slows down because of the drag from the water. So there's my force diagram. Looks a little bit different in this situation. So the curve for this one, though, is different. It's not the same equation. It's similar, though, if you look at it, very similar. The difference is what you had before was you had that velocity times that terminal velocity times the quantity, 1 minus that same e to the whatever. But this one, it starts out at high speed. So that other equation gives you a speed of 0. It starts off at speed 0. You want this to start at high speed and go down. So this is kind of like an exponential decay. It's a very similar equation. Another one that might be useful to put in your memory banks or inside your calculator, but it's very similar looking. Basically, what I want to do in this problem is, again, I want to derive that equation. Okay. So now let's draw or write the net force equation. Well, this one's super easy, right? The net force is equal to the drag. And the net force would be equal to MA. The drag in this case, if you think about it, it's slowing down, so I'm going to have a negative BV in this case. Okay. And so now writing the differential that we don't solve, dividing both sides by m and plugging in dv over dt for the acceleration. Oops, let me go back up. Actually, this would be it. I just needed to divide by m on both sides. That would be the differential that I don't solve. Now solving it, I would want to divide both sides by v and multiply both sides by dt. And this is what I get. This is a little bit easier than the last one in terms of integrating. Integrating the left-hand side, if you remember, the initial speed was not 0 this time. It started at 2.4 meters per second. And it's going to go to some final speed vt. Now, I know it goes to the speed of 0, but we're just trying to find the speed at any given time t. Other than that, this problem's pretty much the same, a little bit easier. And exponentiating both sides, and then finally I get this is my answer, which, if you remember, that was kind of the equation that I said it might be useful to kind of put in your memory banks or in the calculator somewhere. All right. I think, you know what, I think I'm going to stop. Wait a second. Is there another part to this? Oh, yeah. Let me do this part here. Finding the position. So this is the velocity equation. Let's say I wanted to find position. Well, realize that velocity is really the time derivative of position. And so really the v of t is really dx dt. And so I could set that up. If I want to find what the position is at any given time, then I just need to integrate this. And so I'm going to go from some initial position where it started at, we'll say that's 0, to some final position, x of t. And so I just kind of integrate. This is like super easy probably for somebody in calculus. And then plugging in, I get this relationship, simplifying a little bit, and that's what I end up getting. So I don't think we need to do that one. So any questions on, all good?
No.
Okay, so again, just send me an email if you want me to share those with you. And thanks for coming. And so I think then the next time I'll see you then will be Monday for kind of the final exam. Just practice. Think of it as just practice. You don't have to go get an A or something. Just as long as you're trying it, then you got your grade, whatever it is right now. Just think of it as practice. Okay.
Okay. Mhm.
All right. See ya later.
Thank you.
Yep.
Bye.